4 on oscillations. The purpose of this lab was to observe the motion of a mass on a vertical spring as it oscillates in the y direction and x direction by swinging it like a pendulum. The result is that oscillations can be viewed in both directions separately, and energy is conserved in computational model, but it's lost in the real world model. And so our models and principles we use are, of course, a tracker model, GlowScript, period of oscillation equation, spring force equation, velocity and position update, and then our energy principles and equations. So some assumptions we made are that the object is a point mass system, the initial velocity is average velocity for first time interval, and that we're able to calculate our spring stiffness and relaxed length using our period equation and equilibrium position forces after we've done the tracker model. So here are our equations, our period of oscillation, our velocity and position updates, our force of gravity and spring, our potential gravitational energy and our potential spring energy, and then our kinetic energy. So our initial conditions were the camera remained stationary, keeping same frame of reference, and our object dropped, stretching the spring. We were given our mass at 0.402 kilograms, and then we solved for these two using the tracker model in this process. And then our system was mass, earth, and the spring energy, and then the surroundings were our air, which caused some drag, which we can see in our comparison later on. So in our experiment, we would drop the mass from an angle to the side, and it would cause gravity to pull down, and that would be our y direction oscillation. And because we started from the side, it would cause it to swing like a pendulum, causing our x direction oscillation. And then we track the position from the center for each frame and look at the x and y positions. In our GlowScript code, we would calculate the net force with net force, update the velocity and position, update the spring, and then calculate the energy changes using energy principles. So we can see that here. So here's our constants, here's our initial spring, and then here are our initial energies, and then we'd update our forces, apply the momentum principle, and then update our spring and calculate our changes in energy. And when we do that, we are able to see this, and we'll go look at these graphs now. So our model comparison, we can see that the total change in energy does not change at all, meaning energy is conserved in this perfect world. And we can see that it's due to this spring energy and kinetic energy equaling this, and so these amplitudes cancel out on both sides. And then we can see our experiment is actually very close to our model, and so the amplitudes are very, very similar on the x and y positions, and then our periods of oscillation are also very similar. They do have some discrepancies though, and so we'll go over that now. So it was fairly used to predict the actual motion, and energy graph conserved the conservation of energy. Then they only varied slightly. Our periods of oscillations were very similar, and our conservation of energy was maintained. So some errors that possibly occurred was our assumptions for initial velocity, and then clicking the exact center of mass for the tracker model could have caused some issues. And then our calculation of spring stiffness using average period of oscillation over 3 periods, that's not completely exact. And then our result was that energy is conserved in the computation model. However, energy is lost to surroundings in real life, which could account for these slightly different amplitudes and periods in comparison, because there is going to be some drag. And then overall, our model accurately predicted motion of oscillation in x and y directions. And so in the model system, the energy principle is satisfied because no external work is occurring, so change in total energy is always 0. And that's why this and this here would cancel out with that, because the two are positive, one's negative. And then I estimated the period of oscillation for the x direction to be 1.646 seconds and 1.519 seconds for the y direction. They're different because the y direction depends on the spring and gravity completely, and the x direction is going to account for the pendulum motion, which relies on the length and force of gravity.